we'll start. So this is all reaction writing. You'll be familiar with most of it because we've discussed already like one-way arrows, two-way arrows, when to write them. We just did the do now talking about strong acids and weak and bases. So when we have an acid-base reaction, it's just labeled a neutralization reaction because H plus reacts with OH minus and then they form water. So whether it's weak or strong, it's still going to be considered a neutralization reaction. So sometimes the AP exam won't say acid-base, it'll just say neutralization. If a strong acid or base is involved, that means that the KQ is greater than 1 and the reaction goes to completion. So what do we write? What? No, I'm saying for your reaction. One-way arrow. So jot that down. One-way arrow. Anytime that you are using a strong acid or strong base, you're going to use a one-way arrow. So remember I talked about like making yourself a little note sheet for things? For this lecture, it will be really helpful to tell yourself, what do you do when you have a strong with a strong? What do you do when you have a strong with a weak? And kind of label for yourself how to write reactions out. So anything with a strong is always going to be a one-way arrow. It says strong acids completely dissociate. H plus and OH minus ions combine to form water. KQ for this reaction is 1 times 10 to the 14th. We know that. The reactions go to completion. And then everything else in there acts as a spectator ion. Because if you say it's strong and it completely dissociates, then the cations or anions that they're with are going to just be spectator ions. And then the pH is always determined from the excess reactant. So right now, when I gave you pH questions, I only gave you find the pH of, and I gave you an acid. Or find the pH and I gave you the base. Well, what happens when you mix an acid with a base? You have both of them in there, right? So here's essentially what you're doing. Limiting reactant. There's going to be a certain amount of acid. There's going to be a certain amount of base. They mix with each other. And whichever one's left over determines the pH. If you use up all of your base and there's excess acid, then your pH is going to be below 7. If you have excess OH, then your pH is going to be above 7. So you have to just figure out how much is left over to determine the pH. So let's try this one. It says 250 milliliters of a 0.35 molar hydrochloric acid solution is mixed with 150 milliliters of a 0.5 molar sodium hydroxide. Write the net ionic equation for the reaction and find the pH of the final solution. Assume the volumes are additive. Step 1 for writing any reaction. If it is strong with a strong, only write the H plus for the acid and only write the OH minus for the base. Always. If you identify something as a strong acid, then you only write H plus. If you identify something as a strong base, you only write OH minus. Every single time. Oh. Let me try to fix that. And then you'll know that you're going to write a one-way arrow for this. So HCl, what should you write? H plus sodium hydroxide plus OH minus. And one-way arrow is going to yield, I think I was trying to say, H2O, right? As simple as that. So now you're going to look at, though, your amounts that you have. And the amounts that you have are going to tell you if you have which one is in excess and which one's limiting. So it's pretty easy if you just pay attention to the amounts. Sometimes what they'll do for you is just give you equal molar, equal volume amounts. That just means that it's in a 1-to-1 ratio, so you have stoichiometric equivalent amounts. That means that there's nothing left over. So they'll do that just to make it easy for you to write a reaction. But here we're going to recognize that we have a certain number of moles of HCl and a certain number of moles of OH. And then we're going to calculate the excess. So this is giving you the whole ionic. This is not acceptable. If you write complete an entire ionic equation, you won't get credit for it. It has to be only the net ionic when you're done. So that's our final equation there. So the first thing to find the excess reactant is to do what? Find moles, right? You know my technique is to find moles of each, divide by the coefficient, whichever one is the smallest is your limiting. So we're going to take 0.35 molar H plus is equal to X moles over 0.250 liters. And then we have 0.50 molar OH minus is equal to X moles over 0.150 liters. So then we're going to solve. OJ, you got that calculator today? Yeah. So we have 0.088 moles for sig figs, 0.50, and then 0.075 moles here. And then obviously these are both in a 1-to-1 ratio, right? I just want to point out for some of you that if I give you sulfuric acid, it's the only strong acid that we have that dissociates into 2 H pluses. Yesterday I gave you that, and I asked you guys to calculate the pH of an H2SO4 solution. Some of you messed up on that one. But just so you recognize, if H2SO4 is a strong acid, that dissociates into 2 H plus ions. Because it's strong, it gets rid of both of them. It doesn't have weak equilibrium where it just holds on to like one of the H's and then goes to the next. It gets rid of both of them. So if I say this were the same problem, but this said H2SO4, then how many moles of how many moles of H plus would I have if I had H2SO4 here? If this is for one of these dissociation, if I double it, then it would be double the amount of moles. So just pay attention if it's H2SO4. All right, so clearly this is my limiting reactant, and then this is my excess, right? So we label it, and then we go from here. So now we're going to say all of the hydroxide gets used up and reacts completely with this. So what we could do is write an ice chart out. We don't have to, but, you know, we can. And there's no water, so all of this goes away, and it reacts equally in a 1-to-1 ratio with this, right? Make sure you look at your coefficients. You could do an ice chart, or you could do dimensional analysis. You could say 0.075 moles of OH minus, and then just say 1 mole of OH minus goes to 1 mole of H plus, and then that tells us how much H plus gets used. And then you would subtract. It's the same thing that you're doing here. So there's 0 moles left of the OH minus, and then we have 0.013 moles of H plus, and then how many moles of water did we make? Yeah, the 0.075. Now, this doesn't matter because the whole thing's taking place in water, right? So the amount of water that you make in like the whole entire board is my beaker of water. That's how much water you're essentially making, right? Like this is negligible. We're not going to care. Plus you can't find concentration of water because it's in water. So we really just care about our H plus and our OH minus. All right, so then what should the pH be? High or low? Look what's left. This is my beaker. These are what's happening at the end. What's left over? H plus. So the pH should be low. And now to find the pH of the solution, I do it directly from the H plus concentration. If there was OH left over, I would find POH directly from this because these are strong. This said to find the pH, right? All right, so what did I just ask you to do?
Well, we found moles for each of them.
Yeah, so now we need to find pH of the solution. So to find the pH of the solution, you have to recognize that this is now in a larger volume of water. And again, they usually tell you that the volumes are additive. But this amount is floating in. You have to add your volumes up. There's 400. So 0.400 liters will give you the moles. So that's what this is doing right here. We already calculated this amount from here. So we have 0.013. Divide that by 0.4, and you should get 0.033 molar H plus. All right, so now to find the pH, you just do negative the log of that. There's 2 sig figs, so there should be 2 decimals in your pH. Does that make sense? The next type of problem that you're going to get is a weak acid with a strong base. right? So then just think of it, there's only really 3 types of problems. Strong acid with strong base, then strong acid with weak base, and then strong base with weak acid. Okay, so I wrote this already for you here. It says, when you have strong with strong, you only write the H plus for the acid, and you only write the OH minus for the base. If you have a weak acid or a weak base, you're going to write the formula as it's given to you. So for a weak, you write the formula as given for the acid or base. Okay, so, Brian, there it is, right? Okay, so I hear myself when I sometimes post them on YouTube, and I always start with, okay, so we know that strong bases completely dissociate, so we're going to write OH minus. And then each OH minus rips an H plus off of the weak acid molecule, but we're going to write the weak acid molecule as the formula given. So if it's H3PO4, we're going to write H3PO4. We're not just going to write H+. Make sense? And then this will produce water and the conjugate base of the weak acid. So then we'll have 2 more parts on the product side. So take this example. Equal volumes of 1 molar, that's nitrous acid, because that's nitrite, and 1 molar potassium hydroxide are mixed. Write the net ionic equation for the reaction. Identify the aqueous species that have the highest concentrations at equilibrium. So following these rules, is this a weak or strong acid? Weak acid, so we're just going to write it together. So HNO2, AQ, plus. Is this a weak or strong base? Strong, so what do I write? OH minus. Do you write a 1-way arrow or a 2-way arrow? Huh? 1 way. Because anytime you have any strong, the strong is going to be strong enough to rip the H plus off. Right? So you're going to write a 1-way arrow. All right, after you write that, recognize then that this OH, because it's strong, rips off that H plus and makes water, and then what's left? NO2 minus. That's it, the conjugate base of the weak acid. Does that make sense? What is still floating in our beaker that we didn't write? K plus, right? Because it's a spectator ion, it's still floating around. So we had equal molar amounts, which means that this is in there, rips off all of this, and makes this. We don't have a concentration of this. So if we're trying to identify in our beaker what has the highest concentrations, what should they be? So if we were doing limiting reactant like we just did, all of this would go away and all of this would go away. So there's none of this left and there's none of this left, because it all went and made this and this in equal amounts. So this would be minus x 0 plus x plus x. So this is still floating around, and this would give me that same concentration as the K plus. So it's both K plus and NO2 minus are floating in the beaker. We don't say water because water doesn't have concentration, right? So that's what the question is going to give you, is equal molar amounts or equal volumes of the same amount, so that you recognize that all of your reactants go away and they're forming products equally. All right, you try this one on your own. Equal volumes of 1 molar phosphoric acid and 1 molar sodium hydroxide are mixed. Write the net ionic equation. Identify the aqueous species that have the highest concentrations. So our reactants are weak acid stays the same as the formula is written. We identify it's a strong base, so we just write OH minus. OH minus rips off the H plus. All right, here's what's key. They are in equal amounts. So you only have enough OH to rip off how many hydrogens? 1 hydrogen, good. So what's your product? not plus, minus. Because the H is the positive. So if you take an H away, it's going to make it negative, right? So you end up with water and H2PO4 minus. Now, what if I said that I had 2 molar sodium hydroxide? Then what would this be? HPO4 minus 2. And if I had 3 molar, it would be PO4 minus 3. And we would end up with 2 waters, 3 waters. Huh? Oh. Just looking ahead. Does that make sense? All right, so then what's the species that have the highest concentrations? Yeah. What do you think has more, Na plus or H2PO4 minus? Which one is, we're going to say that they're equal, but in theory, what technically could be higher? So this is a weak acid. In water, does this experience dissociation? Some. Really little, right? We have a Ka2 and a Ka3, and we know that they get smaller and smaller each time. This definitely does dissociate a little bit more into HPO4 minus 2 and then PO4 minus 3 on its own just because it's sitting in water. But it's really, really minimal, right? So we're going to say that this and the Na plus have the same concentrations, but you could be approached with that question and say, in theory, which one should be higher, and it's this one because that doesn't dissociate anymore. You love it? What? It's not. All right, so this is exactly what we just talked about, so quickly jot that down, and I'll put the answer up. All right, so did we all get this one? Any questions? And then if it's triple, then you know that it's going to take off all of the H's. Yes?
Why would they have the same concentration as 1 if the NaOH concentration is higher?
Oh, for the ones that have the same concentration? Let me see if I made myself a note here. Because you'll have double the Na plus, double the water, but you would still end up with double the amount. Like if you made an ice chart, all of this would rip this off and make this. Like if you were doing an X, 2X, this would end up giving you, yeah.
Yeah, but if you have double the amount of NaOH, that means you have like 2 Na. But 2 OHs only make 1 HPO4 minus 2.
Yeah.
So it should be
Right,
NH
because it's
double.
pulling off both of your H's. That is a good point. Yeah, I would agree with that. Because even if we did like a calculation here for moles, that this was like say this was 0.2 moles and 0.1 moles.
Yeah.
0.2, 0.1. I think though if you do this, let's pretend that we're doing it as an ice chart. I get what you're saying. I just want to just double check here. So if this was 0.1 moles and this is 0.2 moles, and then we divide this by 0.2 and 2, that gives us the same amount here, right? So then these are technically in equal molar amounts. So then they both get used up completely, so we end up with 0 and 0 down here. Then this would be your plus 2x, and then this would be your plus x.
Yeah, so well, water would be
So minus x minus 2x, and x is 0.1. So that would still be, 0.1. So it would be less. Yeah, so what you're saying is true.
yeah.
Right, like calculation-wise too, you can see that this would be double this. This would end up being like 0.1 moles, but this would still be 0.2 moles. Good catch. Good catch. Higher, yeah. Let me mark that down for myself too. Yeah, just because of the ratios. So if you are on this slide with us, we're just going to cross off HPO4 minus 2 because Na plus is going to have the highest concentration. Thank you. All right, next. 20 mils of a 0.15 molar potassium hydroxide is added to 50 mils of a 3 molar acetic acid. Find moles of OH added, find moles of acetate in the solution. So this is going to lead us into eventually where we're going with buffers. And even beyond that, like we're just going to end up making ice charts for a ton of stuff. So it's really important to know how much of the weak acid that you end up with on the product side. So we're going to calculate using moles. So find moles of OH added. Really simple, right? So just going to throw that in there, calculate it, and you get 0.03 moles. The moles of OH added have to be equal to the moles of the acetic acid that it's ripping the hydrogen off of, right? So it's going to pull off, if we were to write the reaction, it's going to pull off that H out of the acetic acid every single time because KOH is a really strong base. So the moles of OH added are going to be equal to the moles of the acetate in the solution because, let's just jot it down, this is the reaction where it makes water and acetate is left over. So however many moles we add here, which was 0.030 moles, is how many moles are going to react with this. This is 3 molar, so you can tell that that's definitely an excess there. So we end up with all of this going away, and then it forms this, because it's a plus X on this side. So the concentration of OH in there, assuming it's the limiting reactant, is going to be equal to the concentration of the acetate, or the moles of acetate in the final solution. So every hydroxide will take an H plus to form that, and there are 0.03 moles of acetate in the solution. This is still doing like a limiting problem. It's just recognizing that acetate or acetic acid is in excess. All right, so now we're going to switch, and we're going to do strong acids with weak bases, but we're going to follow the same rule. If it's strong, we're only going to write OH for the base. H plus for the acid. And then weak, we're going to write the formula for the base as given. Remember that weak bases are usually nitrogen-containing compounds, such as ammonia or anything with a nitrogen, or the conjugate base of a weak acid. So let's try these. Equal volumes of NH3 and HI are mixed. Write the net ionic equation to identify the species with the highest concentrations. So NH3 should be written as NH3. Oh, I just want to go back real fast. This has a incorrect.
Yeah.
It should say, or the conjugate bases of a strong acid. Yep. Cross off weak acids and write strong acids. I have that in my notes too. Okay, back here. So we're going to write ammonia as it is, and then what do we write for HI? H plus. What else could you write? You could write H3O plus if you wanted, right? And then you're going to write a one-way arrow or a two-way arrow. One, and then you're going to rip off. The H plus gives it to the NH3. It donates it. It forces it to take it. And then you end up with that. So then think about what your concentrations are at equilibrium. So they are equal molar amounts. So what should be floating around? I minus and NH4 plus. Yep. Good. Okay. If you just write H plus, it's just going to be NH3 plus H plus yields NH4 plus, or NH3, yeah. You don't have to write it with the water. All right, so here's a really interesting sort of tricky one. First thing about it is you have to recognize, that's why I gave you for your do now, that potassium carbonate is in fact the weak base, right? And before my do now, how would you have recognized it? You have to think about what happens when it goes into water, and then what is it considered. And so it's hard, remember, to recognize, like we know that carbonic acid, H2CO3, is not one of my strong acids, but yet you wanted to call that a strong base early on, CO3 minus 2, but it's not because it's not one of my strong bases, so you can't. So when I say to write the formula as given for the acid or base, you do, unless, of course, it's with a spectator ion. And what is this one with? Potassium. So we're not, like for this example, we would not write K2CO3 plus H+. Why am I not going to write K2CO3?
K
Spectator ion. K is soluble, always. So just from general solubility rules, you're not going to write it. What I mean by write it for the acid or bases given is because you're going to do that for most of your acids. And for like your nitrogen-containing compounds, you're going to do that also. Unless it's with a spectator. So you need to just make sure if it's with a spectator, group 1A, then you have to dissociate it. Then dissociate. So really when we write this out, we dissociate the carbonate to CO3 minus 2. We still recognize that it's a weak base because it certainly isn't a strong base. And then we have our H pluses. So just pay attention that this is 0.2 molar and 0.1. On your quiz for Monday, you should probably circle them so that you pay attention to how many H pluses to add into your reaction. So if this is taking 2 H pluses, that means it donates 2 of them to the CO3 minus 2 and makes carbonic acid. Right, the AP exam loves this one. So when they give you carbonic acid, you can never write it. Never write carbonic acid because carbonic acid always dissociates into CO2 and water every time. So if you write H2CO3, it just means that you didn't remember this rule, even though the reaction's right, because you have to take this and then break it apart like this is showing you. So then your final reaction is this, and then CO2 plus extra water there. They always give it to you, either in like a multiple choice problem. Sometimes I would say it could show up in a free response, but not really. So definitely multiple choice, they will do something like this. They usually ask you like, what's the observation of this reaction, and what would your observation be? That's not an observation though, because it's in solution, it's in liquid. Bubbles, that's what they're usually going to look for, is that you recognize that carbonic acid produced bubbles, right? So yes, gas is produced, but that's not, you're not going to see gas. So observations have to be using your senses. So make sure that you recognize bubbles would be produced from this one. And I definitely am going to give you one of these to make sure you pay attention to your carbonic acid. All right, so try this one. Equal volumes of a 1 molar and a 2 molar are mixed. Write the net ionic equation and identify the species that have the highest concentration at equilibrium. So try on your own. So your reactants, you have K3PO4. This is, if you stick it with with water technically, this came from a weak acid, but even though we think that, it's not a strong base, right? It's not one of your hydroxides. And this is a spectator, so what do we write for this? PO4 minus 3. And then what do we write for HBr? 2 H pluses, right? So either you write H3O plus or you write H plus. And then what do those H pluses do? They force themselves onto the PO4 minus 3, but only 2 of them. So we still end up with a negative charge on the H2PO4 minus. So make sure you pay attention to that negative, right? H pluses are positive. They neutralize the negatives. But if there's an extra negative left over, it's H2PO4 minus. And then we make our 2 waters. All right, so at equilibrium, sitting in the beaker, what's in the highest concentration? Let's just draw our beaker. What did you say? There's something more. So we dumped in here, and we ended up with K plus floating around. PO4 minus 3, though, gets completely removed, doesn't it? And turns into H2PO4 minus. And then we have Br minus floating around. And then all the H plus turns into water. So we have these 3 things floating in there, but they're not equal. So which one's the highest concentration? Yeah. So why is it K plus and not, originally we say, all right, Br minus, because we know that this is going to make the same thing that happened before in the other question. This is going to be in the lowest amount, right? Because this goes away by x minus 2x plus x plus 2x, and so this is a small amount. And then bromide is 2 molar. This is only 1 molar, but what happens when you dissociate this? 3 K pluses. So that's going to be triple the amount, and then this is only 2 of them, right? So you end up with K plus being greater than Br minus, and then H2PO4 minus. This time this slide's right. All right, moving along. Weak acid, weak bases. So what do you think you do here? You're going to use the same rules, except down here. So you write the formulas as given, unless they're with spectators, and then what do you make sure you use? Double way arrow. So anytime you have a strong, no matter what, if there's a strong present, it's a one-way arrow, but if there's no strong present, then it's going to be double way arrow, and we just write these as a proton transfer. Proton transfer means hydrogen just gets donated over to something else. And then the base is accepting it. So we have a 0.2 molar aqueous ammonia and 0.2 molar acetic acid. So we literally write them as they are. So NH3 plus Chiku, double way arrow, and then the acid donates to the base and the base picks it up. So this H from the acid donates to the ammonia, and we get NH4+. Make sense? So it really comes down to like just memorizing what's right here on the board. I mean, it's not that much information to pay attention to, but and then just moving your hydrogens around the entire time. All right, these we've done before. We've done this, some cations acidify solutions. We did this when we did the reactions, and we talked about how that can happen. And so think about water. Is this where I want to work on this one? I guess I could. Just recognize that water has its own OH and H plus system in it, right? So like we know this, but I don't know that you recognize, due to polarity, these become positively charged and these become negatively charged. So if we have cations that have an ability to pull on this negative, it will rip the OH part off and dump the hydrogen. So it's possible that some compounds can acidify solutions in terms of making more H plus available in the solution. So it says here ammonium nitrate is added to water. What do you know about nitrate? It's always soluble, right? We're not going to write nitrate with water because that's just going to make nitric acid, and nitric acid's a strong acid, so it's not going to stay together anyway. You can never write a strong sticking together, right? So this is just soluble, so really all that's going into the water is NH4+, and NH4+ can pull on this component here, right, and make your H3O+. Donate the H+. So the pH drops below because there's an increase in H+. Yes. You don't?
No.
None of them? Oh. I know, this thing is messed up. Okay. Let me just sort. Is going to donate its hydrogen to the H2O+, which means to H2O to make H3O, which means that the pH of this will drop. So you'll see on your homework problems, if you flip like all the way to the back, this is sort of where it's going to help you on questions like 22 and 23. It gives you two different types of solutions, and then you have to decide which one's going to end up with the highest pH and which one's going to end up with the lowest pH. So then you sort of have to determine which one is the strongest acid base and how does it behave in those, in water, essentially. So for 22 and 23, put both of them in water and then compare. Does that make sense? Like letter A, 22A, stick that in water and then look at both of those and determine what would happen. We'll go back to it. We're going to spend a lot of time tomorrow in class doing the practice problems. All right. I think you have the next slide. Monatomic cations, right? Okay. So monatomic cations can release protons from water. This is what I was talking about. I got ahead of myself. Cations attract the negative poles of water. The positively charged cation decreases the electron density between this OH bond right here, and then some H plus ions can break free and then lower the pH of the solution. So the ones that do this follow Coulomb's law. So they have a small radius with a high charge. So that means that they have a greater ability to attract this negative pole of the water and pull the OH off. So FeCl3 is added to water. So that sort of doesn't look like anything, right? It's not, there's no spectator ions in there. So really, how would you write this? It's kind of hard to figure that out. So the first thing is, this is no longer part of the curriculum, but you will see it on some questions. They don't make you write these. These are called complex ions. They don't make you write them anymore. They used to. But they do put them on there, and you just sort of have to recognize, oh, this is a complex ion. What it means is that the iron was strong enough to pull 6 waters from that and rip off this hydroxide for one of them. So out of the 6 waters, it has the strength to pull off that one and dump an H+. You don't have to know how to write them, but you just have to recognize that's what it's doing. And so then you end up with an H+, and the pH drops below 7. So you're not going to write a complex ion, but you can write Fe+3 plus OH minus, and then show, plus water, then show that it makes FeOH, and then dumps an H+. So you can write it like this. And then I'm going to write an HOH for you so that you see that. So you could write like an FeOH3 plus H+. So that you would, this is for you to recognize that the system would become acidic because there's H+ floating around. So the ability to release protons from water increases as the ionic radius decreases, right? Because you get greater Coulombic force of attraction. And then as charge increases, same thing. Remember, Coulomb's law is charge over distance. So force of attraction is charge over distance. Conjugate acids of strong bases will not affect pH. So group 1A cations, calcium, strontium, and barium, the larger radon, the small net charge, it doesn't affect the pH. Okay, here's why. If you get these together with water, and this is where students make a mistake on this exam, these, if I give you these strong bases with this is not going to change this because say I get calcium +2 and it pulls on this and attaches to this and then you go and write this on your exam. What's wrong with that? It's a strong base, so it doesn't actually it can't form the H+ to acidify the solution because it's not going to acidify a solution. This is a strong base and it's always going to dissociate into these two things. It doesn't stick together. It has such strong dissociation that you never end up with this and you never end up with H+ floating around because the OH will eat the H+ again. So you can't acidify a solution if it's a strong base. That makes perfect sense when I say it, except you try to do it on an exam to see like, oh, does this acidify the solution? So if you just keep telling yourself, never write a strong acid or strong base together, then you would say, oh, this dissociates. Okay, now there's OH minus and H+, so this can't possibly acidify it. That's what this means. You cannot write them together. Maybe write that for yourself. Do not write together. Because they dissociate. The same thing is true for some anions make solutions basic. If the anion's strong enough to pull on the H+, then it dumps OH minus, right? So some anions do have the ability to pull. Which anions do not? Strong acid anions. So the conjugate weak base would not be able to do that because if you have any of these anions, which come from strong acids, any of them would, if you wrote it as it picking up an H+, it's going to turn into the strong acid, and strong acids completely dissociate. So you're not going to end up with OH minus floating in solution. So it will not work for any of the conjugate bases of a strong acid. It only works for things like this, where you put acetate in. acetate pulls one of the hydrogens and makes the solution basic. So the pH would rise above. But say we did it for like Cl minus plus H2O, and you were trying to do this for yourself, you would think to do this, you would put this here, and you would write this like this, and you'd say, oh, the solution's basic because I make OH. No way, this dissociates again. You never can have this floating around as a whole component in water. So if it breaks apart into H+, then look, this eats this, and there is no base in your solution. Get it? You don't have to memorize which anions and which cations. All you have to memorize are your strong acids and your strong bases. All right, the sulfate anion is a very weak base because it comes from such a strong acid there. It's just showing you the dissociation. It says this will possibly accept a few H+ ions to go backwards to make the HSO4 minus 2 because H2SO4 is the strong acid, not HSO4. So it's just saying like there is a possibility of SO4 minus 2 picking up some of the H pluses and making the solution basic. Right? So if it does that, I think it shows you, it doesn't show you that. If you put this in water, it's just saying that some of this could possibly form and make the solution basic. Possibly. All right, metal oxides are basic. So we're almost done. I realize you guys have been listening for a long time, but I'd rather practice most of your problems tomorrow than lecture again. So I just want to kind of get through it. You are going to get this and the next slide definitely on my quiz. So one of these questions. You have to just, for these, like all of your reactions, memorize this one. Metal oxides can form solid hydroxides. So what you have to do is take your metal oxide and break it apart into the cation and anion, which is Mg plus and O minus 2. And then react the O minus 2 with water, right? We're not going to, well, I'll show you. O minus 2 reacts with the water, and it makes the 2 OHs here. So think of it like this. And then you have O minus 2, which is your negative, is going to pull on this. Do you see that? The slightly negative, slightly positive pulls on each other, and you make OH minus. And then what gets dumped? OH minus, which is why you end up with 2 OH minuses. So that should make that clear so that you don't have to actually like memorize that step. It's just pulling it. So you dump off 2 OHs, and now this is floating in the water, so you just combine your reactions here. This is the combination of this plus this. This is the combo. So we have MgO solid plus water, and then these form a solid. So magnesium hydroxide forms a solid. The slight solubility of solid hydroxides increases as the OH concentration in the solution increases, and that's just using equilibrium rules. So if this increases hydroxide, it drives the reaction to the left. So just make sure you memorize that one. So the same thing here, potassium oxides dropped in water. You're going to do the same process as you just did before. So go back here and look. Potassium oxide's K2O, so write K2O solid. And here's the key thing. I am not writing O minus 2 here. Why? Even though potassium is a spectator ion, why am I not writing O minus 2? So this is from your reactions section. Do you remember why? Because it's a solid. So it doesn't mean that it's dissolved, right? It's not dissociated. So you write K2O. Just like we did back here, we wrote MgO because it said a solid. Or this one says a solid. So you write K2O plus H2O, right? Down here, K2O plus H2O. This part is to show you that when it gets dropped in water, this is what dissociates, right? Like you don't have to write all this, but this is the thought process. This is what you need to come up with. So this is a solid, we write it first. It gets dropped into water, so we react it with water. The O2 minus pulls on the H and makes its own OH plus another OH, so we get the 2 OHs and we end up with 2 K pluses left over. And then, same as before. Actually, no. That's it. Why are we not making a solid here? It's a strong base, right? If you put KOH together like we did in this last slide, we put MgOH2 together, that wouldn't make any sense because it would be a strong acid, a strong base. Okay, these are just the last two slides. So some salts have an acidic cation and a basic anion. Solutions containing these salts tend to have little or no effect on pH. So it's just both of those last few slides combined. So we have NH4 plus and acetate. So both of them are this one's gonna donate an H, then this one's gonna pick up an H, and we're gonna end up with H plus and OH minus floating around in your products, and then they eat each other and it's neutral still. So these really have no effect on the pH of the solution. And then the last one, CuF2, same thing, Cu plus 2, F minus. Cu plus 2 is going to attract what in water? OH. Some of you are following. Cu plus 2 attracts OH minus, so it's going to dump an H plus. What does F minus attract? H plus, and it's going to dump the OH minus. So you would end up with H plus floating around from this, and you would end up with H plus, OH minus floating around from this, and then they eat each other, and it's neutral. So if they're both basically this weak acid, weak base, it's not going to really have much effect on the pH of the solution. Following this all? Okay, we're done.